Boom.
All right, good morning, ladies and gentlemen. Today we're going to be using the video, The Story of the Electric Field, as visualized by Michael Faraday, in order to help you guys learn about the electric field. And throughout the class time today, we're going to be going from the video to the slides that I have here over on that side, and we're gonna do this with you. All right. So here we go.
This is not loud enough.
Let me turn the volume up. Wait, here we go. There we go.
In the game of ice hockey, scoring 3 goals in one game is called a hat trick. I'd like to try to pull off a kind of hat trick today. I'd like to tell you what an electric field is, solve a problem in field theory that Isaac Newton seems to have had a great deal of trouble with, and introduce an important mathematical idea known as Gauss's law. All of that will turn out to be easier than it sounds because it all flows from the vivid imagination of a great genius named Michael Faraday. Faraday's life would have embarrassed the most shameless novelist. He began in the most modest circumstances, and he had very little formal education. And he eventually wound up being apprenticed to become a bookbinder. But he was intent on self-improvement, and he started attending public scientific lectures at the Royal Institution in London. And he was so enthralled by those lectures that he begged for the chance to do the most menial kind of work at the Royal Institution. And he did begin there, and he eventually wound up as the professor of the Royal Institution and the most famous scientist in all of Europe.
Okay, I'm going to stop this. This is an inspirational story. Back in the 1800s, if you wanted to go to school, you had to pay for it. And if you were not well off, then you started working when you were like 11, 12, 13 years old, which is what happened to Faraday. And the beautiful thing about his experience is he worked as a bookbinder and was able to learn how to read by reading the books that he was working on. It's an amazing story. And he had no mathematical training. Imagine that.
Wow.
Throughout his career, Faraday understood mathematics so poorly that he couldn't read the scientific papers of his own competitors. And yet he had an intuition that got him to the core of every scientific problem. It is one of the greatest ideas that flowed from that intuition that we want to speak about today. It's the idea of lines of constant electric force radiating everywhere throughout space.
In the field of physics, surely no tool has dug up more scientific truth than the sharp spade of mathematics. Yet when he uncovered the field theory, the groundwork from which much of modern physics grows, mathematics was a tool that Michael Faraday had to work without. But he was exposed to one idea that was essentially mathematical in nature. In 1789, Charles Augustin Coulomb confirmed what the scientific community had suspected for years. Coulomb finally demonstrated that the electric force is inversely proportional to the square of the distance between the charges.
Does that look familiar?
It does.
Here is what Coulomb did. He established that electrical forces obey the inverse square law. Okay, now what does that mean? Well, this is an example where you have the square of the distance on the bottom of the fraction. So this is Coulomb's law like we used before. Don't worry about this. It's called R hat. It's the vector direction symbol for this. Yeah.
Now, what is the inverse part? Is it just because this is under? This is
It's
not.
on,
It's
so
on the
what
bottom?
this means is that the distance gets bigger, the force gets smaller. That as the thing on the bottom gets bigger, the whole thing gets smaller. It's like, why is
Opposites.
1/4 less than 1/2?
Gotcha.
As elegant as Coulomb's experiment was, the concept, the idea of the inverse square relation, had been a major scientific notion for some time. A century earlier, in fact, Isaac Newton's theory stated that the fall of an apple and the orbit of the moon were both consequences of the same basic laws. And one of those laws, the law of universal gravitation, states that any two masses attract each other with a force inversely proportional to the square of the distance between them. But this was a difficult law to apply, even for Isaac Newton himself. To make the point, he'd have to show that when an object's attracted to the Earth, it acts as if all of the Earth's mass were concentrated at the center.
Okay, so here's an important point. Newton said that gravity obeys the inverse square law, measured from the center of mass, so that when you use his law of universal gravitation, you have to assume that all the mass is concentrated at one point. That will allow you to use the r squared on the bottom.
Oh, so it's kind of like all of our mass is right here?
Yes.
Oh, okay, got it.
Yeah. And he invented calculus in order to prove this.
Woohoo!
Right.
And more difficult, he'd have to rationalize what he called action at a distance, a phrase meaning that such bodies as the Earth and the Sun apply forces directly to each other, even though they're separated by millions of kilometers, with no tangible connection between them. Though the great genius was often a bit testy, even he himself might have come to admit a certain dissatisfaction with the idea of action at a distance. Perhaps somewhat defensively, in the Principia Newton wrote, "I have not been able to discover the cause of those properties of gravity, and I feign no hypothesis." With that famous phrase, "I feign no hypothesis," Newton felt no obligation to explain by either physical or mechanical means.
Yeah, let's talk about what's important about this, and that is Newton had his law of universal gravitation that said how strong gravity would be between two masses a certain distance apart, but he had no idea how that force was exerted through empty space. And this is a very important aspect of science. If you can't explain, if there's something that you don't understand, you have to be honest about it. You can't pretend that you know if you don't. And Newton's statement about "I feign no hypothesis," I have no explanation, is an important characteristic of every scientist. You know what you know, and what you don't know, you're honest about.
The law of gravity. To us, it is enough that gravity does really exist, he added, and act according to the laws which we have explained. Obviously, that was enough. In England thereafter, the law of gravitation was the law of the land. And by the 19th century, with the law of gravitation firmly established, Newton's followers had discovered that electricity and magnetism obey similar laws. In all of them, the force decreases with the square of the distance. The similarity is amazing.
It is amazing.
The question is, why?
Whoa.
Perhaps because the inverse square law is related to a simple geometrical property of three-dimensional space.
Very important point here.
And perhaps because these forces aren't the only things that diminish with the square of distance.
The essence of the inverse square law can be seen in the concept of flux, the Latin word meaning flow. Light flows out from the sun equally in all directions. As it spreads out, getting farther from the sun, its intensity decreases. But imagine a sphere enclosing the sun. All the light would pass through the sphere, no matter what its distance from the sun. And the area of a sphere grows as the square of its radius. So the amount of light energy per unit area decreases as the square of the distance.
Good visual.
Okay, so here's our point here, that as light moves out from the sun, the farther out you get, that intensity of all the light spreads out over spheres. And the larger the sphere, the less the intensity. You want to show them how this works?
Yeah. Okay, so here is our sun. Okay, I'm gonna go ahead and put it on. Ooh, that's bright.
Oh, that's bright.
It's really bright. Okay, so just like in the visual, we have the little things popping out of here, right?
All the light that's coming out of that is on that little sphere.
Yeah, it's really bright. It's hard to look at, to be honest. Just like the sun. Don't look at the sun, right? And so in the video, we put over a sphere here, and the sphere has a certain area, and
all the light coming out of the bulb is spread on that surface of that sphere, and so the intensity of a square unit area is less than it would be
if it was just on this thing, right?
Yeah.
Okay. Now if we put this guy on here, I'm gonna get that on there. What do you notice about how bright the light is?
It is much less bright.
It's much less. It's a lot dimmer, right?
Well, what it is you have the same amount of light that's now spread over a larger surface area. So that per unit amount of intensity is less than it is. And if you pull it off and go back to the middle thing, oh, that's bright. Turn that sucker off.
Yeah. So you can see that as we have more surface area, as we get further away, the intensity of that light decreases. And
Let's stop this.
sorry.
So the area of a sphere is 4 pi r squared. And so the farther out you get, as the radius, the distance gets larger, the intensity falls off proportional to the square of the distance. So that's the heart of the inverse square law. That's right, I like that.
Okay. All right, ready over?
The inverse square law wasn't the only provocative idea to which Faraday was exposed as a young man. By 1810, he was a regular visitor at the Royal Institution, particularly at the lectures of the institution's legendary professor, Sir Humphrey Davy. Chemist and natural philosopher, a scholar who was knighted, made a baronet and president of the Royal Society. Davy was the very crest of British science. With his own research as the subject, Davy spoke as the world's authority on every element from sodium to potassium.
Okay, I'm going to stop here and let's go back to the story of Faraday. He was uneducated, he was self-educated, and he was attracted to the Royal Institute, where they were monthly lectures given by the best scientists of the day. And Faraday went to the Royal Institute and said, give me a job. I'll do anything. I want to be here. So I like sweeping and emptying trash cans. And he worked his way up to the point where he was the scribe. He was the one who would write down the notes for these lectures. And then from those notes would be these publications would follow. And it was an amazing way to get an education without having to pay for it.
Before he couldn't even read and write, right?
Well, he could read and write because, before, but he didn't have much education at all because he was from a poor family.
Yeah.
Chlorine to iodine. Davy became a scientific father figure for Faraday and remained a mentor and enormous influence for almost 20 years. Although the relationship was at times a rocky one. But under Davy's influence, in the golden age of chemistry, none shone brighter than Michael Faraday. He discovered benzene, liquefied chlorine gas, and developed new alloys of steel. The list of his remarkable accomplishments as a chemist goes on and on. Nonetheless, in 1821, Faraday set aside his work in chemistry. In that year, Ørsted discovered the effect electric current has on magnets. And while that effect can be seen clearly now, in 1821, it was still a great scientific mystery. Indeed, Why would the compass needle line up perpendicular to the electric current?
So what you have here is a wire that and it's parallel to the compass needle, and when they run a current through the wire, all of a sudden the compass needle responds because there's a magnetic field that appears around the wire.
Sparked by curiosity to begin with, and asked by an editor to write an article that would end the scientific confusion, Faraday set out to solve the mystery for himself. Faraday saw the possibility of harnessing the force of an electrical current and invented a device to do it. That device happened to be the first electric motor. How did Michael Faraday manage that? Perhaps because, being unable to analyze them mathematically, Faraday was able to take these circular magnetic forces at face value. In any case, to Michael Faraday, electricity, as well as magnetism, applied real forces in space, and he began his study of them with a number of assumptions.
So here is the big idea. Just like magnetism, just like we saw with the bar magnet, electric charges exert forces in space. Okay, well, how can you tell a force is exerted? Well, ladies and gentlemen, we're going to see the zombie hand. You ready?
Anywhere in the vicinity of an electric charge, a small test charge experiences a force. If it's due to only one charge, the pattern of forces detected by the test charge is simple.
Okay, now notice the test charge is far away and the force is small. Watch what happens when it gets close. It gets big. Now, what kind of force is this?
Electrical force?
It is an electrical force, but there are two kinds. Which is it?
Oh, so this is the original charge. So
Yeah.
is this the test charge?
That's the test charge.
Okay.
So that's repulsion. So it's repelled away.
Okay. Because the arrow is going this way. If it was attraction, it would be going that way?
That's right.
Okay.
And so here's the idea. The only way we know an electric field exists is because it exerts a force on a positive test charge.
Wait, I have a question.
Yes.
So is the force still there if the test charge, is the field still there, the electric field still there if the test charge isn't there?
That's a wonderful question, and the answer is yes.
Okay.
That if this is our originating charge right here, the field around it was there even before the zombie hand brought in the test charge.
It's there no matter what, right?
Yeah, and here in this video, the red is positive and blue will be negative. Mm-hmm. And so this is a very important thing. I know you're writing this down. And the positive test charge will symbolize as Q prime, okay?
Dash on it. Okay.
Yep.
Ready?
Pay no attention to this music.
The pattern's more complex for two opposite charges.
Attraction. Attraction. Repulsion and attraction.
Or for two charges of the same sign.
Repulsion, more repulsion close, less repulsion far. This is kind of like what we saw with the bar magnets when we had the same ones.
And more complex still, for more complicated arrangements.
I hate this music, I hate it.
I kind of like it.
But in any case,
You haven't
here's the
listened to
point.
it in 20 or 30 years.
Even if the test charge isn't there to feel it, the pattern of forces can be imagined to exist everywhere in space.
Okay, even if the test charge is not there to feel it, the pattern of forces is still there. And so making a map of the forces on a test charge shows the existence of the electric field. We're going to use the uppercase E to represent the electric field. And so how do you make a map? You move the test charge around and record the forces that are exerted on it.
This is the essence of the idea of the field.
Oh, I see.
And although Faraday only imagined it,
What's
the field can also be expressed mathematically.
acts on a test charge at each point in space is equal to the
Whoa. Before the zombie hand comes in and does some math, here's the important idea. The force on a test charge is determined by Coulomb's law.
We know Coulomb's law.
Yeah, we have got some experience with it. So now, let's talk about what we're seeing here for just a moment. This is the Greek letter sigma. It means the sum of all the forces due to all these charges. So for each charge, we're going to ignore this. And if you ignore that, look, there's Coulomb's law.
Oh, yeah. Our constant 9 times 10 to the 9th, and then our 2 charges over the radius squared, or distance squared.
And this I is for the test charge. And this is the distance to the test charge from the originating charge. We'll talk more about this in a minute. Now, watch what the zombie hand is going to do.
Test charge times a quantity due only to the other charges.
Whoa, what just happened? He pulled it out and put it in front. What's the next one?
Oh, thank you. I keep forgetting. There we go.
That quantity is the electric field.
Okay.
Oh, look at that.
The force on the test charge depends on the quantity of charge and the strength of the electric field.
Okay.
So how much charge you got on the test charge and the force that it experiences gives us the electric field. How could we solve this for E?
Oh, I know how to do that. We ready?
Well, now hold on a second. We're going to stop right here because there's a problem to do.
There sure is. You're right. Oh, no. One more slide.
Oh, okay.
Yep. In fact, I think we
Well-
go to the next one here.
Yeah, we're going to
So
stop
right there. Okay.
Yeah.
Here is our last slide right here. And you know what? Let's go ahead and open up this. And then we can, because I think the next slide is, we're here, and then we go to that
Yep.
question. Okay. Whew, sorry, guys. All right. So, we just said that the force of the electric field. Thank you. I was like, wait, where is it? We just said that the force of the electrical force is equal to the amount of test charge times the electric field.
Yep, the strength of the electric
Boykin,
field.
you just asked how can we solve for the electric field?
Yep,
Okay, well, we just divide by Q,
that's all.
right? And so it looks like this.
So
and
write this down. This is
yeah.
an important equation
I'm going to write it down over here. So we said the
because
electric
this unit is about the electric field.
is equal to the electric force, electric field, electric force.
Force électrique.
Yes, and you have to say it like that. I think that's not.
Charles
that's right.
Augustin Coulomb.
Okay, so it says a test charge with a charge of this many coulombs experiences a force of 0.6 newtons. What is the strength of the electric field at that point? Okay, well, let's see. So we are given the.
The force is 4 times 10 to the negative 5 coulombs.
Okay. Oh wait. No, that's the charge.
Oh, I beg your pardon, my bad.
Okay, so I'm gonna go ahead and put that at the bottom right here. Okay, so 4 times 10 to the negative 4th, you said? Oh, 5th.
5th.
Coulombs. And then what is the electrical force, or the force? Oh, 0.6 newtons. Okay. And I can just plug this into my calculator, and I get, oh, that's not it, 0.6 divided by 4 times 10 to the negative 5th.
Yep.
Negative 5th, and oh, I keep doing 4, and that gives me 15,000.
15,000. And what are the units going to be?
Well, is it a Newton Coulomb?
Newtons per coulomb.
Newton.
That means that for that electric field at that point in space, for every 1 coulomb of charge you put at that point, it'll experience 15,000 newtons.
That's a lot of force.
That's a lot of force. That's a pretty big electric field.
Okay, so now we're gonna go back over here and start at 1335. Is that right, Logan?
I think we just pick it up.
Just pick it up where we left off.
Well,
It says to
let it roll here. Let's see what happens.
all right. Oh,
Faraday never arrived at that definition of the electric field.
Because he didn't do math.
But by seeing both electric and magnetic phenomena as forces in space, he managed to see further than his peers. As a result of this, and many other discoveries, he eventually became director of the research laboratory at the Royal Institution. And succeeding Davy, he became the professor there, as well as a member of the Royal Society. But it was as researcher, rather than instructor, that he saw deeper and deeper into the invisible forces of space. To Faraday, the 1/r² force between electric charges suggested that the force must be applied by something radiating outward from charges. Something which, like light from the sun, never stops and never ends in space.
So here's a positive charge.
As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path.
And that's a single charge.
These lines of force would begin only on positive charges and end only on negative.
Okay.
Oh, this looks familiar.
So here's our definition of the direction of the electric field. It's out from the positive and in to the negative. Out from the positive and into the negative.
Like light from the sun, never stops and never ends in space.
Here's a positive charge coming up. Out from the positive.
As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path.
Out from the
These
positive.
lines of force would begin only on positive charges
Into the negative.
and end only on negative ones.
Here's two positive ones. What's it going to look like? Well, it's going to go out from the positive.
And they would flow smoothly through space, never crossing or tangling.
Oh.
What does that look like, boys and girls?
Looks like repulsion.
It looks like a picture of repulsion that we saw with the magnetic field between the same bar ends.
So that's important. Magnetic field and electric field, they're not the same thing, but they have similarities.
They are
there.
very similar.
No matter the configuration, the charges would have a characteristic pattern of lines. The force they applied would be strong near the charges where the lines are crowded together,
Big force,
and weak far from the charges where the lines are farther apart.
small force. Okay, I'm going to stop the zombie hand right here and say that the direction of the electric field is the same as the direction of the force on a positive test charge. Okay, so the zombie hand is holding a positive test charge here and moving it around in space. And whatever direction that arrow is pointing, that's the direction of the electric field. The length of the arrow shows you how large or small, how intense the field is, the magnitude, and the direction of the arrow is the direction of the electric field. Away from the positive.
ability to apply a force resides at each point in space, and
Small
the force
arrow.
arises from the intensity of lines,
Lines far apart,
regardless of the location of the charges that create them.
close together, the higher force. Okay, so we got a positive test charge. What's the direction of the electric field right here? That way. Okay, so we have a field here that's caused by something up here. What is up here at this point? What is going to be right here? Positive or negative charge?
It's going to be positive, right?
Because we got repulsion.
Yeah.
It goes out from the positive and it's looping down toward a negative.
Even without such space-age graphics, this is how Faraday pictured the electric field.
Okay, boys and girls, thank God we're done with this.
Woohoo! Although very exciting. Mr. Boykin was like, this is going to be a boring video. I was like, should we tell them? He's like, no, they'll figure it out on their own.
Yeah.
That's funny. Okay, so an electric field
Electric
charge.
charge.
what do we call this again?
That's the originating charge.
Originating charge produces a field around it where forces are exerted. We were going to do the Van de Graaff.
Well, you know, I think we should wait on that because it's not working very well. So here's a positive charge, even though it's blue.
Yeah, dang, they switched the colors on us. Yeah. And what do we notice about the electric field here? It's going out.
Away. And if it's a single isolated positive charge, then it goes out like spokes on a bicycle.
Looks pretty cool.
Yeah.
Very geometric. And then for the electric field, for a negative charge, they're going to be going in.
So the shape of the field is the same, positive and negative, but the direction of the field is different. And how do you know? Well, imagine the zombie hand coming in with a positive test charge.
Yeah, if it comes in here, what's it going to do? If it's
close to the positive,
yeah,
it'll be repelled.
If
and if it's close to the negative, a positive test charge will be attracted.
Ah, okay. See, if I brought a positive charge in here.
What Faraday was saying is the intensity of the field is symbolized by how close the lines are together. So the field is intense here, less intense farther away.
Okay, that makes sense. All right, here we go. We just have, again, some more definitions here.
Got to know the players if you want to play the game.
Yeah. So this is our originating charge, and, you know,
Q sub 0.
We saw those in the video. And then the positive test charge doesn't always have to be positive.
Yes,
right?
it does.
Oh,
it is
does.
always positive by
That's a
definition,
very good point.
and it's the zombie hand that was moving it around.
Bring it in. Okay.
And that's Q prime.
Q prime, that's what we call it. All right, here we go. Coulomb's law predicts the force between the originating charge and the test charge.
So before we had Coulomb's law with Q1, Q2, now we're getting more specific about which charges.
Yeah, this is our originating charge, and this is that positive test charge that we are bringing in.
But the zombie hand moves around.
The zombie hand, I used to love it. Okay, practice problem. Okay, so
let's use Coulomb's law.
Let's do it. Okay, so Coulomb's law, we know that we're trying to figure out the electrical force, and we know that it equals that K constant times Q original times the
Q prime,
the test charge, over the D squared. Now, does it matter if it's D squared or R squared?
D squared, R squared, same thing.
Same thing, okay. So 9 times 10 to the 9th, that's what we get. That's what that K is.
Yep.
Newton's
meter squared over Coulomb squared.
Over Coulomb squared times. And
Q original is negative 3 zeros and a 5.
1, 2, 3. Oh, 1, 2, 3, and a 5 coulombs. And then multiplied by our test charge.
5 times 10 to the negative 9. Oh, and the originating charge is negative. Did you get? Yeah, you
I got
that
negative there. Okay.
And how far apart are they?
Okay, they're 0.025 meters squared. 0.025, and then I put meters and I square that at the bottom. Okay, so let's go ahead and plug this in.
What kind of force we got?
Well, it's going to be attraction.
Yep.
Right? Okay, so how do we know that? Negative a positive attraction. Okay, so 9 times 10 to the 9th times a negative 0.123505 times a positive 5 times 10 to the negative 9th, and I'm dividing that all by 0.025 squared, right? Looks good to me. And I get negative 36.
Negative 36 newtons.
Negative 36 newtons. Okay, so here we go. I'll just say my electrical force, is negative 36 newtons.
And that means that the positive test charge is going to be attracted to that negative, so it's going to be in. I've got an idea. Let's put that into what we've got on top here.
Attraction. Okay. Oh, right up here?
Yeah, let's just erase what you got from that previous
That's a good
thing.
idea. Okay, so we got negative. All right, so we've got negative 36 newtons here.
Yep. That's the force we just calculated.
Okay.
And the test charge is 5 times 10 to the negative 9.
Coulombs. Sweet. So once we have the electric field here, once we have that force, if we know the test charge, we can figure this out. Negative 36 divided by 5 times 10 to the negative 9th.
Yep.
And I get, that's a big number, negative 7.2 times 10 to, let me count my zeros.
Holy schmeisel.
Negative 7.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's a big
Newtons
number.
per coulomb. Okay, and that negative means that it's going to be toward the originating charge. That it's attraction.
Yeah, okay, that makes sense. All right, so we just did this.
Find it.
Good job, team. Okay.
We're
so
psychic.
The intensity of the field depends on the size of the original charge and the distance from it.
Yep.
Yeah.
It's a simple thing.
Yeah. Okay. The electric field just is.
It exists.
Right? It exists, and whether or not the test charge is nearby or exists at all, it's still there. The test charge just allows us to see it.
Yeah, so here you've got a positively charged thing, and even if you don't have a test charge there, there's an electric field around it.
A test charge, Q prime, measures the presence of the electric field point in space.
Yep.
It just measures it. Okay.
Yeah.
So let's check this out. So if the force, the electric force, is this, let's go ahead and put this here.
Well, I notice here you've got the red test charge on the top
Oh yeah.
that you're multiplying, and then you've got the red test charge on the bottom that you're dividing. What does that mean?
That means they're gonna cancel out.
Yeah.
Okay, let's go ahead and show them.
So there's another way of talking about the electric field other than the force on a test charge. And that is, if you don't have a test charge.
What if you don't have a test charge? Oh, look at this little guy.
The balloon still works.
Okay, so what were we just saying here?
We
okay.
want to solve.
So we have the force over the test charge, right?
Yeah.
And we know that the force,
We'll just write it is equal to KQ.
Oh, yeah. So the force is equal to KQ like this over D squared, right? That's that top right here.
Yeah, and then divided by.
Q prime.
So can you cancel anything, boys and
Yeah,
girls?
so what happens here, it gets flipped, right? And this is
Yeah.
like being over 1, so
Yes,
it's
it
really
is.
like times 1 over Q1.
Well
We just
done.
ignore that. And then these cancel. So we're just left with this.
So that's another way of saying the electric field. So you got
Yeah.
two ways of saying it. The first one is if you have a test charge and you can measure the amount of force. And the second one is if you don't have a test charge, but you know how much, and that should be Q original.
Oh, sorry, right here. I just realized that. I was like, wait, hold on.
If you have the quantity of charge on your originating charge and the distance, then that's it.
Sweet. So you can get it both ways. Awesome.
So I think that's it. I don't think we should have them do any homework.
No.
I think that was enough effort just maintaining your attention span.
Today was excruciating enough. All right, guys, have a great day.